All right, welcome to lesson 6 where we talk about the conditions of a wire. So if you're working on harnesses such as the one that's in front of us, this is an ISX 15 harness. If you're doing your meter checks, so you've been given your manufacturer's check, maybe you've been even given the ohm rating for each of the wires, which is great, but you're doing your pin-to-pin checks. So you're going to check your connector pins to your tail ends, so on these 3-wire or on a 2-wire device like this one right here. And maybe you've even gone out and bought yourself a set of probes, which you'll probably need to do this right anyway. But be careful of which ones you buy. These needle probes can actually be too thick for doing good checks. They don't fit very well, and they cause you to push in too hard. And what happens is you spread the pins, you spread the socket inside the connector, and you can cause more harm doing the check that way. So be careful of that. If you can buy the individual test tails that go into the sockets for either the amp seal or the Deutz or the weather pack, that is better. Alternatively, you can try and do back probing, but on connectors such like this, where it's got a big rubber boot, you do have to pull the rubber boot all the way back to gain access to that connector. So something to be aware of. So we're assuming you have your meter, we're assuming you have your tool, and we're assuming that you have a harness that you're needing to test. We're going to get to the 5 conditions of a wire. So assuming we're working on a harness similar to one I've drawn up here, I just have an example that I've drawn a section of it from pin 10 to pin 14, going to 2 different devices. One's a 2-pin device, one's a 3-pin device. And let's assume we drew our little blue meter up on the top right there. So that's fine. Typically, what we would do is we would end up disconnecting these ends. So you disconnect your 2-pin device, you would disconnect your ECM connector or your controller connector, and you would run your red lead over, you would poke into that connector pin or socket, and you would take your black lead and you would run over here and you would poke in the same way. You'd set your meter right here to its ohm function, and what we should expect, this is sort of our first, this is what we're trying to do here. We're trying to figure out what do we expect to see. A reference that we have when you come for our in-person class or that we have available within the course here is a guide that sort of shares what is the normal resistance across 1,000 feet of wire. And ultimately, when we do the math, if we drop down to about a 16 gauge wire on a 53-foot trailer, we should expect to see 0.07 ohms of resistance. Okay, so if you're working with your typical harness wiring, that's 16, 14 gauge, 18 gauge, for automotive application gets smaller, we're expecting to see less than 1/10 of an ohm of resistance on a wire across 50 feet. And so if you're working with your normal vehicle harness, what we're expecting to see for resistance from pin to pin is truly 0, depending on how your meter or how accurate your meter reads. So we would expect to see 0 ohms. Now, that's a good wire. So that's one of our first conditions. If we think about the 5 conditions of a wire we can have, the first one we can have is just straight up good. Now, do we know it's perfectly good? Not actually yet, because there's still another condition that can come up that can create a problem for us, and that is a short wire to wire. So what's possible is that somewhere in this harness, we actually, or in multiple harnesses when they come together, because we know these are not all individual wires in our vehicle. We have branches that come together and branches that split off. So you'll have a point, if this is a 70-pin or 120-pin connector that we're only seeing a section of, at some point you're going to have all 120 of those wires come together, and it's possible that we have a rub wire-to-wire connection. And so let's just draw that right here, and let's just say we have our fault in blue. And what if we have a condition where we have a short wire-to-wire? And so that would be our second condition. First condition is good. Second condition would be a short wire-to-wire. The only way you're going to know whether you have a short wire-to-wire is to actually leave this red lead here and to move the black lead into another pin location. So if you check from 10 to A and you get 0 ohms, but then you check from 10 to B and you also get 0 ohms or you get 0.5 ohms, what that would tell you is that you have a short from 10 to not just to A, but also to B. And so you might need a schematic to understand, should I have continuity there? But on a device like this, a 2-wire device, no, you shouldn't. Now, here's where some people would disagree and say you don't have 2 different problems here, because A, on most devices would be a positive, and B would be a ground. And so I've split the short wire to wire from the short to ground for the reason that depending on if you have a positive switched or a ground switched device, you can have an unwanted on that doesn't create an open like a short to ground does. So what I'm saying is, if you have 2 devices that are externally grounded and you short wire to wire, what'll happen is you'll have a crosstalk situation. You hit the brakes and your horn turns on, or you turn your turn signal on, and while your turn signal on, your wiper's going. That would be a short wire to wire that's not typically a short to ground. So I've mentioned short to ground. So let's talk about that. Number 3 would be a short to ground. Now, a short to ground almost always results in an open. So a true short to ground, let's say I do have battery positive coming off of 10 and it's going into A. Let's get rid of this short wire to wire for a second. And let's say we have an unwanted, so faults are in blue, unwanted short directly to ground. So what does a short to ground look like? Well, it's typically where your harness, the P-clips, the zip ties, the ladder clips have come loose, not been replaced, not been put back, or broke, and the harness has rubbed against the chassis. And so now our wire is making contact to frame ground, and we have an unwanted connection to ground. And electrical's lazy, it will take the path of least resistance, so give it a ground, it's going to take it. So this short to ground, condition number 3, will always result in 10 seeing an overload condition. So on the back side, if we had a fuse anywhere in this circuit on the positive side of pin 10, if we had a fuse in there, that fuse has now failed open. So a true short to ground, where battery positive or supply positive is being sent out and has a path straight to ground, results in a circuit failure of an open. So short to ground results in the open of either a fuse, or if this is a controller and that's let's say a 5-volt reference signal coming out of pin 10 instead of battery voltage, what can happen is that channel within the ECU can actually overload and fail open. Now, some circuits have what's called a current limiting resistor inside their controller, which means that if we did run short to ground, it would fault and it would display a code, but it would not fail the channel, and that's helpful. But not all circuits in controllers have what's called a current limiting resistor within them. So it is possible that we have a short to ground that results in a failure of the open of pin 10 or an open of the fuse or circuit protection or breaker that is ahead of that. Okay, so now we have conditions 1 was good. We have good continuity on the wire, but we weren't quite done. 2, short to wire to wire, so making sure we don't have unwanted connection. Now, condition 2 can actually make condition 1 be bad. So we can say, hey, this is a good wire, but when there's a short wire to wire, it's now no longer a good wire. We have to fix that. Condition 3 is a short to ground that usually results in an open, failing the channel of the controller or failing the circuit protection ahead of the controller. Condition 4 is the other term that I used, and that would be the condition of being open. So we run into opens all the time. So either a short to ground results in an overload of the circuit, the wire overheats, it breaks or melts, and it fails in the open state. We can leave poor wire 10 alone. We can pick on another one. So let's say we're doing the same test now all the way down to pin 12, and we're going to run this black lead all the way down to pin A. And so now, if we have an open, what we would have expected was a 0 number. If we have an open, our meter will no longer read 0. it will actually read OL. And some of you have meters that read OFL for out of limits. So out of limits is air gap, infinite resistance. And so that's a condition we have in a wire where we have an open. This is usually where a physical break has happened, a current overload protection has happened or was triggered, and now it's open so we can, like we talked about with a fuse right here. But in any case, what we're seeing when we check the wire is that the resistance on that wire is infinite. That is a condition of our wire being an open. Opposite of an open, actually no, it's not opposite of an open at all. It's actually not quite yet an open. And this is one of the troubling spots for everybody. And that would be number 5, and that's high resistance. So if you have a high resistance condition in your wire, so let's move down to wire 13 now. Let's move our meter leads. Let's come all the way down to 13. Let's get rid of this wire off of A right here, and let's come down to B. And so once again, we'd expect this to be 0 ohms. But remember we talked about there's a chart that tells you what your normal resistance is. But let's say we do this check from 13 to B, and we end up getting 5 ohms instead. So the actual, we read 5 ohms. And you'd think, well, 5 ohms is not going to be that much, but we could do the Ohm's law calculations, and it would depend on how much current is on that wire, but we are creating a voltage drop from pin 13 to B. Now, the voltage drop matters because the voltage we pass through multiplied, or the potential that's there, multiplied by the current we allow through, that would be a better way to phrase that. So the potential that's there multiplied by the current it passes through equals the wattage that's going to be created. And anytime we have unwanted resistances, so that would be like a big old resistor. This is that 5 ohm resistance we're finding in there. Anytime we find a resistance in a wire, that is going to be a point of heat creation. And so now you can have a little heater going on inside the harness, which makes the insulation brittle. So even if it doesn't get hot enough to melt, it gets hot enough that the insulation of the wire starts to get crunchy. And then any movement of the frame starts to result in that insulation cracking and breaking. When it cracks and breaks, that's how we start getting our wire-to-wire condition that we had over here. And so any of these resistances can't really be ignored. They're supposed to be 0. If they're not 0, it's because there's something going on. Now you could ask, what causes this high resistance condition? Well, it could be a wire. Instead of all of the strands of a wire, if we look at like the cross-sectional area of a wire, we could see that somehow there was some damage that happened to the wire. And instead of all of these strands working, we're down to 1 or 2 strands carrying all the current load. That would be an unwanted resistance. Our wire is getting narrower, and so it's building a resistance. That would be a problem. Another one could simply be rub through, so we're rubbing through. The harness is damaged all the way to that 1 or 2 strands. We can also have bad practices of previous technicians, where they went and bought themselves these leads, and you know what's great about these leads is they're sharp. And the technician has decided instead of getting to the end of the connector, they were simply going to stab the wire itself. So once we stabbed the wire, we now created a place for water to migrate in. Water creates oxidization with the presence of air in that insulation. And now instead of having our copper conductor, we have a copper oxide going on. And now it starts to get thinner and thinner. And again, we're down to 1 or 2 strands doing all the work. The rest have corroded away. And so now we have a high resistance condition again. So bad technician practices can do it. Physical damage to the harness can do it. And just general oxidization. A lot of the time, technicians may see a voltage drop across a wire showing a resistance value in there. And they did it when they were back probing. So they used a back probe and they checked the voltage drop. But then when they disconnect the connector and they look it over and then they put it back in, the voltage drop goes away. And if that's the case, then your fault, your problem, I should have made this blue. Our faults were going to be blue. Our faults can actually be at the connector itself. And so sometimes you will remove the connector, clean them with an electrical contact cleaner, reinstall them, and that will be enough to fix your problem. You went from a high resistance condition to no longer a high resistance condition. So our conditions then that we'll see as we work through testing our harnesses is you're going to find wires that are good. And you're going to have to know what a good wire is. And that means that it has continuity and very low resistance, zero essentially for most of our vehicles, and no connection to an unwanted wire. So that would be good. Then we have a short wire to wire, and that's any time we have an unwanted connection that can result in another device turning on the headlights, turns on the wipers, that kind of a thing. We can have a short to ground. That is anytime our battery positive or 5-volt reference voltage has an external, unwanted, unplanned connection directly to battery ground, and it usually results in an open in the circuit because of an overload. As soon as we give a free flow to ground, it takes it all, and it's going to overheat that wire, resulting in a failure of our circuit protection or the channel on the controller. We have an open, that's number 4. Our open condition is physical damage most commonly, or a pulled pin and socket. Sometimes the lock mechanisms on our pins and sockets inside our connectors are not perfectly fastened, and when we reconnect, the pin and socket is pushed away. And so since they don't mate when they're connected, then it becomes an open. So that's another problem that you have to look for. And then a high resistance that can be caused by oxidization or rust, essentially damage, physical damage, rubbing through, poor connectors. Sometimes you'll find somebody that's tried to use the wrong size pin and socket to build their connector, and they trimmed off all the extra wires so that they could hopefully make it work. All of our wires have a current rating, and if we go any smaller, then we create an unwanted resistance. So this is the 5 conditions of the wire you're looking for as you go and test your harnesses.